Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this section of the course, we are going to do a quick review of the prerequisites needed to understand this course. The major focus of this review section will be logistic regression. As you may recall, logistic regression is also known as the neuron, and a neural network is simply a network of neurons. So as you might imagine, this is pretty important. We'll start this section with just a basic discussion of what machine learning tries to do. Just as a reminder, I want you to remember that machine learning is nothing special. It's nothing but a geometry problem. Then we'll look at the mechanics of logistic regression. First, we'll look at how a logistic regression model makes predictions. After that, we'll look at how to train a logistic regression model. And if you forgot, that's the same outline that this course follows for neural networks. First, we're going to look at how to make predictions using neural networks. Then we're going to look at how to train a neural network. This is, of course, because in order to train a model, we first have to be able to make predictions from it. This is so we can compare the predictions to the true targets to get the error. So hopefully you're comfortable with this format and it makes sense to you, because that's what we'll be following throughout the course. Now keep in mind that this is stuff I've assumed you already know, as per the requirements listed in the course description. So if you see anything new here, that's probably not a good thing. That's not to say you can't catch up, since I know many people who have. But what I am saying is that you have to be prepared to put in some extra work to fill in missing background knowledge if you need to. Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we're going to review some of the most basic principles of machine learning. You absolutely have to understand this if you want a solid grounding on how machine learning works and what it can be used for. The key point of this lecture is that machine learning is nothing but a geometry problem. That's right, it's nothing more than just a bunch of dots on a grid. It's what we do with these dots that makes machine learning what it is. The most basic machine learning problem looks something like this. We have some input on the x-axis, and we would like to be able to predict the target, which is on the y-axis. So as an example of this, we would be trying to predict someone's weight from their height. We know that generally speaking, taller people are heavier because they have more mass. Of course, there are exceptions to this, such as a very tall, skinny person or a very short and stout person. So that's why these points don't fall on an exact line, but they generally follow the same pattern. Our goal is to find the line that best fits to our data. We call this the line of best fit. So we would write out our model as y hat equals wx plus b. And here x means height and y hat means predicted weight. Of course, in many real-world problems, you might have more than one input. For example, you might be trying to predict the price of a house given the number of bedrooms and the average family income of people in that neighborhood. In this case, we'd write it out as y hat equals w2x2 plus w1x1 plus b. We could also write it out as W transpose X plus B for short, and here W is a vector and X is a vector. In fact, we usually have more than one input to try and predict the output from, so you should get very used to using this vector form of these equations. Now as a convention, we usually use the capital letter D to denote the size of W and X. And by the way, they both have to have the same size in order for the dot product to actually work. And when we have d greater than 1, we no longer have a line of best fit, but a plane or a hyperplane. In other words, it's still a non-curving object, but it has more dimensions. So this problem of trying to predict a continuous value is called regression. In the past, we've studied linear regression because it provides the groundwork necessary to move on to deep learning. We also have the problem of classification, which is what we'll focus on mostly in this course. For classification, we're trying to predict a category. For example, given a person's height and weight, we can try to predict whether or not they have high blood pressure. In the past, we used logistic regression for this task. Again, logistic regression uses a line or a plane for the model. But instead of this line or plane trying to predict a value, it now provides a boundary. We can say anything on one side of this line means not high blood pressure, and everything on the other side of the line means high blood pressure. This is called binary classification because we're trying to predict the label out of two different categories. In this course, we'll explore how to go from 2 to any number of categories. One important point that I cover often is that all data is the same. I hope you've realized that in the discussion we just had about what machine learning is trying to do, there's no reason that the data had to be from the examples I used. So I said let's use height and weight to predict high blood pressure, but that need not be the case. What if we switched height to be weight and weight to be height? That's totally fine, it's still a geometry problem. What if I completely change the problem? Let's say I want to predict whether or not you will pass your math exam. As input, we can take in the number of hours you studied and your grade on the midterm. But realize that this only changes the semantics of the problem. It does not change the mechanics of the problem. The problem still is, we have these red dots and we have these blue dots, and our job is to find the line that best separates the red dots from the blue dots. In other words, we use the phrase, all data is the same. It doesn't matter if you're trying to predict whether or not you have high blood pressure or whether or not you will pass your math exam. It doesn't matter if your problem is a finance problem or if it's a biology problem. All data is the same, and machine learning is nothing but a geometry problem. So to summarize, I hope this helped you to remember what supervised machine learning is and that it's not anything magical. It's just a geometry problem. And because of this, we know that all data is the same. You can plug in any data from your own area of interest. None of the code has to change and none of the algorithms have to change. Machine learning works no matter where your data comes from. Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we're going to review logistic regression, which is used for classification. Logistic regression is the most important prerequisite for this course because a neural network is really nothing but a bunch of logistic regressions put together. So as we discussed, in logistic regression, we separate the blue dots and the red dots with a line or a plane. In other words, this line or plane will take on the form of W transpose X plus B equals 0. Note that this expression is going to give us back a number, but we know that we would like to be able to predict a category. So how do we go from a number to a category? Well, the idea is we're going to encode our two categories as 0 and 1. Then we pass W transpose X plus B into the sigmoid function, and this always gives us a number between 0 and 1. We interpret this as the probability that y equals 1 given x. Note that you can only get exactly 0 or exactly 1 when the input is negative or positive infinity, due to the asymptotes on either side of the sigmoid. So as you can see, the sigmoid takes in any real number, and if that number is greater than 0, then it returns a number greater than 0.5. If the input is less than 0, then it returns a number less than 0.5. And typically we use 0.5 as our threshold. So if p of y equals 1 given x is greater than 0.5, then we predict 1. Otherwise we predict 0. We can put this all into one line by using the round function to get the prediction. Now when we're working with Python, we know that it's not good to use for loops if we can avoid them. For loops are generally slow, and NumPy does a lot of optimizations under the hood so that we can avoid them. As an example, if you take the dot product of two vectors, by definition, you could accumulate the sum of each element-wise multiplication. But as you can see, this involves a Python for loop. Not good. What we'd rather do is use the numpy dot function, which does the exact same thing. Similarly, in machine learning, we usually want to calculate the output for all of our samples at the same time. So typically we have a big matrix called X, which is of shape n by d. N is the number of samples and d is the number of features. And by the way, this brings up another important convention. By convention, we typically use lowercase letters when we're talking about a single vector, which is a 1D object, and we use uppercase letters when we're talking about matrices, which are 2D objects. So we would like to calculate all n predictions simultaneously. One way to do this would be to use the formula we looked at previously, loop through each of the n samples, and accumulate the output one sample at a time. But notice that there's a for loop here, so we know that this is not ideal. What we'd rather do is calculate all n predictions simultaneously. We can do this with the code, sigmoid of big X dot W plus B. Now there are some things you have to keep in mind in order to understand why this works. First, you'll notice that the W appears on the other side of X this time. This is because X is n by d, and W is just a 1D vector of size d. In order to do a proper matrix multiply, the inner dimensions must match. So the second dimension of X must be d in order to multiply it by a thing of size d. In other words, we can't put W on the other side, because on that side the dimension of X is n. Also note that b, the bias term, is just a scalar. After multiplying X by W, we get an object of size n. But how can we add a scalar to an array of size n? Well, that's because NumPy does broadcasting. So the same single scalar gets added to all n elements of X times W. So to summarize this lecture was all about how to get the output prediction of a logistic regression model. The big question is, what is W? How do we choose it? This is called training the model, and that's what we'll be discussing in the next lecture.